All right, problem 4.42. We are asked to predict products of precipitation reactions or potential precipitation reactions. And we're also asked to write 3 equations for each, what they call a molecular equation, what they call a total ionic equation, and also a net ionic equation for each of these, okay? Again, predicting products of precipitation reactions is governed by the so-called solubility rules, which you'll need to be familiar with. They are in table 4.1 of your textbook, okay? You want to memorize those because they are absolutely crucial to predicting the products of precipitation reactions. So in part A, we have 2 things that are combined. Calcium chloride, cesium phosphate. Notice both are aqueous solutions. Again, all of this precipitation chemistry always is in aqueous solutions. So if I was actually doing this in lab, I'd have 2 different beakers. Both of them would have water as the solvent. Beaker 1 would have some calcium chloride in it. Now that would be dissolved because it's a strong electrolyte, it dissolves. The other beaker would have this stuff, okay? Also dissolved. I'd mix them together, I'd mix all the ions can switch partners and perhaps form a precipitate. So let's try to predict what can potentially happen in such a case, all right? Now again, if we're dealing with a precipitation reaction, the key to that, to understand, is that we could have so-called double displacement occur, where the ions switch partners, okay? That can occur because, again, all these ions are hydrated, they're all mixed together. Nothing that stops that from happening. So if that's the case, then one potential product could be CsCl. Now, think about writing the formula for this first. Is that the correct formula? I would offer that it is, because I've got a cesium plus 1 ion, chloride minus 1. Charges are balanced, we're good. Now the other possible, and that would be aqueous, okay? So CsCl, AQ. Okay? Now the other possible product forms from the other ions, which are left. Calcium and PO4, phosphate. Okay? Now I have to ask myself, is this the correct formula for calcium phosphate, or does it need to be changed or modified? Okay? And how so? To do that, you need to know the charges. Okay? Now calcium is pretty easy to figure out. Calcium is just a 2+. Phosphate, though, comes in a group. It's one of those polyatomic ions. Those guys, again, in these reactions, the polyatomic ions for precipitation reactions, they stay together as a group. And maybe they form a precipitate, but this PO4 doesn't change. It comes in the group. Maybe it reacts with something, but PO4 stays together, that ion. Now, PO4, what's the charge? Well, maybe you have your list to memorize, which hopefully you do, but if you don't, you can kind of infer what the charge is because you know that cesium is +1, so the phosphate has to be a -3 here, which in fact it is, okay? So phosphate's -3. Calcium, I said, was +2. So we have a little bit of an imbalance right now is that we don't have enough positive charges, right? We have to do something about that. And I think the easiest way to solve this problem maybe to say Ca3, PO42. That makes 6 negatives and 6 positives. And we've got ourselves a balanced formula. Now, the next step, after you predict what can possibly form, is to figure out if something will form. Okay? Remember, to do that, you have to assess whether one of your potential products is considered insoluble. If it is insoluble, a precipitate will form. Now look at this one, cesium chloride, and I realize right off the bat that this is a soluble compound. Group 1 metals form soluble salts. Almost all chlorides are also soluble, except for chlorides paired with heavy metals. This is soluble, so I'm going to put AQ behind it. It actually would exist as ions in solution. Now, when I started this problem, this ion, phosphate, really jumped out at me because phosphates kind of have the reputation as not being all that soluble unless they're paired up with a group 1 metal or else ammonium, because ammonium salts are soluble. So if I'm pairing this up with calcium, I'm highly suspicious that this is an insoluble compound. And sure enough, if I check my rules, it will be an insoluble compound. So what I'm going to do is put the S behind that to denote the phase of that being a solid. And that's my precipitate that forms here. So in fact, a reaction does occur here. We form that calcium phosphate solid precipitate in solution. But we have a bit of work to sort of tidy up here before we move on. Because what we're going to need to do is to balance this reaction before we do much else, okay? Now that's going to be a little bit of a mess because the stoichiometry of combination of different things, but we can probably figure this out, okay? So I look over, I'm going to start with phosphate, okay? Because again, I can group that together and say that phosphate's here, phosphate's there. How many copies of phosphate do I have? Well, over there I've got 2. And right here, right now, I've just got 1. Now I can fix that by putting a 2 out front here. Now I've got 2 phosphates and 2 phosphates in a balance, okay? And I can move on to other elements as well, okay? Maybe I do calcium. On the right, I've got 3 over there. To balance that, I need to put a 3 here. Right, now, what elements are left? Okay, well, I've got the cesium and the chloride. So let's take a look at that. Looks like I've got 6 chlorides. I've also got 6 cesiums. Oh, so this isn't so bad. I can just put a 6 there and bring this equation into balance. Now a bit on terminology and vocabulary here, okay? The problem asks you for the molecular formula, or the balanced equation, the molecular equation, the total ionic, and the net ionic equation. What I just wrote here, your book is going to call this molecular equation, okay? I don't necessarily like the terminology there because usually we consider ionic compounds as being formula units, not necessarily molecules. But the idea is that if you're writing this molecular equation, you show everything kind of paired up together as a formula unit, okay? Now, the other types of equation are commonly discussed. The next one would be total ionic, okay? The total ionic equation. In the total ionic equation, you show all substances present as ions, if that's how they exist, in any solids. Okay, so if I'm writing the total ionic equation for this guy, what I would probably write is something like this: Ca2 plus Aq. I'd put a 3 out in front by virtue of this 3. I would combine that with 6 Cl minus. I don't know where to get 6 from. 2 times 3. When this stuff dissolves, all of this is released and hydrated, right? So I've got 3 copies of this, or 3 formula units of this. Each one contains 2 chlorides, so I have 6 chlorides. Aqueous. Move on to the next substance. Looks like I've got 6 copies of Cs plus 1. Aqueous. All this is aqueous phase. So you see what I'm doing here? I'm just writing out, tabulating all of my ions. I've got 2 copies of phosphate. Those are both 3 minus. Aqueous. Write my arrow denoting the chemical change and just continue the process on. On the right, I have 6 Cs plus 1 aqueous. Hydrated ions. I also have 6 copies of Cl. Aqueous. Hydrated ions from this compound. And now what about this last one? On the previous step, I determined that that was going to be my solid precipitate. Solid precipitates appear in the total ionic equation as solid precipitates because that's how they're really existing. So I'm going to actually write this one the same. Ca3, parentheses, PO4, subscript 2, solid. Okay? Because again, the calcium and the phosphate, they bump into each other, they pair up, they form a crystalline solid, white precipitate in solution that exists as a solid. When that solid forms, the ions no longer are aqueous, they're no longer hydrated. Now they exist in that solid crystalline lattice. Okay? So this is my total ionic equation. Now the last type of equation the net ionic equation. Remember, the net ionic equation eliminates spectator ions. Those spectator ions are the ones that just float around the beaker and do not do very much. Okay? The spectator ions, just like a spectator at a football game. They kind of sit there, maybe they cheer and watch, but they're actually not actively participating in the chemistry, so we call them spectators. Okay? Spectators are unchanged before and after the reaction. They should be the same on both sides of the arrows. And if I'm looking for spectators, I see these 6 Cls, and I say, oh, that's a spectator. So it doesn't change. Also, these 6 CS plus doesn't change, right? Spectator ions never appear in net ionic equations. Only the ions which participate in the chemistry. So I bring down the calcium. I bring down my 2 phosphates. Those come down because they're not spectators. Because what they do is they pair up to form my calcium phosphate, my insoluble compound, a solid precipitate. That's my net ionic equation for the first part. Okay? Alright, so that's part A. Let's go through part B real fast, okay? Again, let's start on writing my total ionic here. So I've got sodium sulfide. I recognize sodium sulfide as a strong electrolyte because all sodium salts are soluble. So I know I'm going to have some Na plus ion floating around, and I'm also going to have some S2 minus floating around. Now I'm not putting the numbers out in front right now because I'm going to see what's necessary to balance things in a second. But what I am doing is just making an inventory of all ions which are present. The next compound that we're going to mix with this, and this is all aqueous phase chemistry, zinc sulfate. Okay, this is also going to be a soluble compound. So I have zinc 2 plus aqueous and some sulfate, SO4 2 minus aqueous. Arrow to denote possible chemical change. Let's think about what can happen. If we're going to have a double displacement, the ions switch partners. So one possible product, and I guess I'll go back up here for this, okay? One possible product would be what? Sodium as my cation, paired with sulfate as my anion. Now if I was going to do that, I need to balance the charge. I need to put a 2 right there, okay? Because sulfate's minus 2, sodium's plus 1. That's one possible product. What's my other possible product? Zinc 2 plus being paired up with sulfur to make zinc sulfide. Okay? Let's think about these. Are either one of these insoluble? That's the key question. Now, all sodium salts are soluble. So sodium paired with anything is soluble. Right? So that's just going to be an AQ. Not going to be a precipitate. But this guy, zinc sulfide, it's going to be insoluble, sparingly soluble. So that's going to be a solid precipitate that we're going to form as a result of this chemistry, okay? So that gives us a little bit more hints as to what's going on. Now that we've actually went to write the equation, we can start thinking about balancing things and seeing if things are balanced. So I've got Na2, 2Na, 1 zinc, a sulfate, sulfide. Oh, okay, so I'm already balanced. It saves me a little bit of trouble. And then what I can do is fill in my total ionic equation now by writing 2 Na plus AQ, by writing in a copy of my sulfate, 2 minus AQ, and by finally writing my zinc sulfide solid. It's going to be my precipitate. So now this is my total ionic equation, and everything should be balanced. If I write my stoichiometric coefficients over here, so I had 2, I still have 2, sulfide just have 1, my zinc I've got 1, my sulfate I've got 1, everything should be balanced, okay? So now I'm writing the last equation, the so-called net ionic. And remember, the net ionic equation only shows the net chemical change that occurs in a precipitation reaction. The spectators are excluded. So I can quickly identify sodium as a spectator. Sodium ions will always be spectators because they always form soluble salts. Okay, they're never insoluble. What else is a spectator? It looks like maybe sulfate's a spectator, huh? So I'm going to get rid of that one and that one. And then the net chemistry that's occurring here is the zinc 2+ aqueous ion combining with sulfide 2- to make zinc sulfide solid precipitate. That's my net ionic equation. So again, practice this because predicting these products, writing these equations is going to be a key skill for the homework. I'd also guess you'll see this on an exam.